Hello and welcome to our next lecture on cyclic codes. Let's look at a brief outline of today's talk. We would consider what is a ring and how they are related to fields. Then we will look into polynomials and use them as building blocks for our cyclic codes. We will look at the division algorithm, and then using these mathematical tools we would introduce the concept of cyclic codes. Finally, we will have some examples. Let us look at a quick recap as to what we have done already. We have spent quite some time looking at linear block codes. We figured out why they work. We looked at some specific examples of Hamming code, the LDPC codes, MDS codes, and finally, we looked at the probability of residual errors. Having said that, we now move on to this new subclass of codes called cyclic codes. Now, let us define it first. So, code C is cyclic if number 1, C is a linear code. So, we are now looking at a subclass of linear block codes. Whatever theory we have learned so far is applicable to cyclic codes, because C is itself a linear block code. But what is more is that any cyclic shift of a code word is also a valid code word. Alright. So, if A0, A1, A2 up to AN minus 1 is a code word contained in a cyclic code C, then if you put AN minus 1 in the beginning and then shift each one of them by 1, 1, 1, you would end up getting another code word which is also valid. So, any cyclic shift is also a valid code word, hence the name cyclic codes. So, clearly the first bullet tells us that if you take this linear block code, then cyclic codes are necessarily a subset of linear block codes. So, all the techniques that we have learned so far are applicable to cyclic codes, but as we will see, cyclic codes have tremendous error correcting capabilities in terms of burst error corrections. Also, they are very hardware friendly. So, the cyclic codes are a much more powerful class of linear block codes. So, let us look at a quick example. Let us look at a binary code. There are 4 code words in this code: 0000, 0101, 1010 and 1111. The first step is to verify whether it is a linear block code, and then we will look at the cyclic shifts. So, if you see, the all 0 code word is contained, the sum of any 2 code words gives a valid code word, and therefore, we can say definitely this is a linear block code. Now, we do the third check whether if you do a cyclic shift. So, if you put the 0, 1, this 1 here and the 0 here, you get this one, and then any cyclic shift will give you back this one leads onto itself, and so on and so forth. So, any of the 4 code words undergoing any number of cyclic shifts ends up being another valid code. So, therefore, this is definitely a cyclic code. But if you look at a slightly different example where it is an equivalent code, but it is definitely not cyclic. So, because the cyclic shift of this does not yield another valid code word, and therefore, you can verify that this is maybe a linear block code, but it is not a cyclic code. And these 2 codes are equivalent in terms of the distance properties. Both of them have a minimum distance of 2. So, let us now foray into the world of polynomials, which have a very strong linkage to cyclic codes. So, we are going to take a mathematical detour for the next few slides, build up some mathematical tools, and then use it for describing cyclic codes much more efficiently. So, let us look at a polynomial. Most of us already know this, but just for the sake of clarity, f of x can be written as f0 plus f1 x plus so and so forth up to fm xm, and f0 f1 are the coefficients, and the highest order will be the degree of the polynomial. So, please note, if I define this polynomial over GFQ, that means the coefficients here are taken from GFQ, they are the elements of GFQ. and we already know Galois field with q elements, we know the properties. So, this also means that if I can add, subtract, multiply, divide to polynomials, because the coefficients get added, subtracted, multiplied, hence and so forth. Therefore, I will follow the arithmetic of GFQ to do those things. As I said, Fm is the leading coefficient here for the highest degree, and m is the degree of the polynomial, and it is often denoted by dig f of x. Now, a polynomial is called monic if its leading coefficient is unity. So, f of m, if it is 1, then this also becomes a monic polynomial. Please note, in polynomials which are binary, you do not have to worry about it, because it is either a 1 or a 0, and 0 means it does not, that term does not exist. But for a general case GFQ, you will need to have Fm equal to 1 for a monic. Otherwise, for example, GF4, this Fm can be either a 1, 2 or 3, but for monic it needs to be 1, the highest coefficient. So, let us look at an example here, a polynomial over GF8. So, the valid coefficients could be 0, 1, 2, 3 up to 7, and GF8 is 2 raised to the power 3 is 8. So, it is a prime power, and hence GF8 exists. Now, if you look at this polynomial, the highest power is x raised to the power 6, and the leading coefficient is 1, hence it is a monic polynomial. The degree of this polynomial clearly is 6. Now, polynomials do play a very important role in the study of cyclic codes, as we will see. Now, if you say f of x be a set of polynomials, so suddenly we are talking about a set of polynomials in x with coefficients in GFQ. So, x is that indeterminate, right, and capital F of x is the set of polynomials. Now, clearly this set of polynomials is a collection, and the polynomials in this set can be added, subtracted or multiplied in the usual manner, and the arithmetic will be carried over GFQ. So, Fx is an example of an algebraic structure called a ring. We will soon see what are the properties of a ring, and whether it is a field or not is what we will have to verify and check under what condition this collection becomes a field. So, look at some properties of the polynomials. Some of them we know and we use them without even realizing. Then if you see f of x and g of x are two polynomials contained in this set of polynomials f of x, capital F of x, then degree of the product is the sum of the degrees. We know all of this, but please note that degree of f x and g f x, when you add them up, is not necessarily the maximum of degree of f x and degree of g of x, for a simple reason that if both of them are monic, then they will cancel each other out possibly. So, if you see 1 plus x square is my polynomial f x, and g x is 1 plus x square, and if you add them up, look, the degree has actually gone down. So, this is what we know, because if you do binary arithmetic GF2, then 1 plus 1 is 0, and x square plus x square cancels out, and therefore, the highest power of x is 1. Let us look at another example. These are basically refreshing our memory. We know most of this stuff. Consider a simple polynomial f of x 1 plus x and defined over GF2. So, all the arithmetic that we do will be over GF2. So, we can square it. How does it look? So, f x square is you take this and multiply it over, and 1 plus 1 gives 0, and therefore, 1 plus x plus x squared is nothing but 1 plus x square. But just consider 1 plus x as the polynomial over GF3. So, I am now going to square this, but not over GF2, but GF3. Now, GF3 can have coefficients 0, 1 and 2. My polynomial happens to have just one coefficient as 1. So, I would like to square it. So, 1 plus x plus x plus x square is what you get by squaring it, simple multiplication by itself. And now you end up with 1 plus 1, and if you look at the table GF3, which is also modulo 3 arithmetic, because 3 is a prime number, I get 1 plus 2x plus x square. So, same polynomial squared over GF2 and GF3 gave different results. So, this is important to observe that the field is important. Now, let us quickly go over this addition and multiplication. So, you can take two examples, but it is best to show by examples. I have got f(x) and g(x) over gf3. So, please note the coefficients are from 0, 1 and 2. So, gx and fx, and their degrees are also different, but I can always add these two polynomials and we can do it like this explicitly. So, this is a coefficient of x raised to the power 0, I add them up, and then I add the coefficients of x. There is a missing x here, there is an x here, so only x, and so on and so forth, and you get an answer like this. Similarly, I can multiply them, it is a long multiplication, and I carry it out and again use the arithmetic for the GF3 table, and if I do this, I can simply get an answer as a product, and product its highest power is 5, highest power is 4, and it is no surprise that the product has the highest power x raised to the power 9. So, the degrees have added. Okay. So, this is a simple example that you can carry out addition and multiplication, but each time I do the sum or the product, I take care of the table belonging to the correct Calva field. So, we have already established that field is important, and if you square over GF2 and GF3, the same example, but we are trying to emphasize that the same operation over different fields will give a different answer. So, field is indeed very important. Now, let us look at the remaining part, which is the division algorithm. What does it say? Well, it states that for every pair of polynomial ax and bx contained in fx. So, what is this capital F of x? It is nothing but a collection, it is a set of polynomials. Alright, we have already seen that we can add, subtract, multiply. Now, the question is, can we divide? So, clearly division by 0 is not acceptable. So, I have got b of x not equal to 0, and then what we would like to do is, there we say that this algorithm states that there exists a unique pair of polynomials qx, which is called the quotient, and rx called the remainder, such that ax, which is one of the first polynomials, is nothing but quotient into bx, which is the divisor, plus rx, which is the remainder, and degree of rx must be less than the degree of bx, which is the divisor. So, it is stated as an algorithm, it is more like a simple theorem. So, the remainder is also called as the residue, and residue succinctly it is written as r b of x. So, I am dividing with b of x. What am I dividing? A of x. So, if you divide a of x by b of x, the remainder or the residue is called r of x. How is it written? Ax is equal to quotient times bx plus residue. So, we will use this notation many times during the subsequent slides. So, let us look at some important properties of residues. Since I can add two polynomials, the residue of ax plus b of x for fx is nothing but the residue of ax when divided by fx plus the residue of bx when divided by fx. So, this is nice, it can help us solve some of the properties and solve some of the theorems that we will encounter in the future. And the product also holds true. So, if I have a product ax into bx and I take the residue with respect to f of x, it is nothing but the product of the residues and the residue with respect to f of x. So, that is how we get. We will use these two properties over and over again. All right. So, let us look at a simple example. Let us take ax is equal to a polynomial x cubed plus x plus 1, and I have got bx is equal to x squared plus x plus 1, and I am going to carry out all of this arithmetic over GF2. So, it is a long division. I write x cubed plus x plus 1, this is the divisor, this is the dividend, and I just multiply it out. When I multiply it with x, I get another polynomial, because product of polynomials is defined. I subtract it out and I get a residue r of x. So, this simple example shows that we have got with us this quotient and the remainder, and we can clearly write your Ex, the dividend, equal to x plus 1 quotient into Bx divisor plus the remainder or the residue x. Okay. So, this will be required many times when we do cyclic codes, because please remember, we are taking a mathematical detour, we are still trying to study cyclic codes, but these tools that we are revising or gathering with us will help us solve cyclic code problems much more easily. Please note one thing, the degree of Rx must necessarily be less than the degree of Bx, otherwise I could have divided one more time. I keep doing till the degree is less than B of x, okay, strictly less than. Now, we talk about this term called congruent modulo. So, let f x be a fixed polynomial within this collection or set f of x. Now, two polynomials g of x and h of x, both contained in f x, are said to be congruent modulo f x. F x was a fixed polynomial in f x in capital F of x. So, if this is true, if g x is equal to h of x mod f x, and we have this g of x minus h of x is divisible by f of x. So, let us look at this example. Please note, we are trying to define congruent modulo f of x. So, I am taking this h of x and do modulo f of x, that is, you divide it by f of x and whatever remains, and that should be g of x, then they are called congruent modulo. So, let us look at a quick example. Let us say g of x is x raised to the power 9 plus x squared plus 1, and h of x is x 5 plus x squared plus 1, and my fixed polynomial is x raised to the power 4 plus 1, and I will do all the arithmetic over g f 2. Now, you can see that if g x minus h of x, we saw this earlier, is divisible by f of x, then they are written congruent modulo. Now, we quickly go to rings of polynomials and then eventually fields of polynomials. Again, let us be patient and we will quickly link to cyclic codes, but this is interesting stuff. So, if Ax and Bx belong to f of x, capital F of x divided by small f of x, then the sum Ax plus Bx in f x, capital F of x divided by f of x is the same as in capital F of x. What does it mean? Well, we are looking at two polynomials, right, and we are going to look at the sum of these polynomials, but every time we do so, we are taking it modulo f of x, small f of x. So, what is critical is this very interesting polynomial f of x. We are still going to do operations of addition and multiplication contained in this set capital F of x, but now all the operations will be done modulo small f of x, that is, whatever is the residue or remainder after dividing with small f of x is the answer. Okay, and this you can check, degree of a of x is less than degree of f of x. Why? Because we are taking modulo f of x. Similarly, degree of b of x less than f of x, and therefore, degree of ax plus bx is less than degree of f of x. Similarly, the product ax and bx is a unique polynomial of degree less than degree of f of x, right, to which ax into b of x is congruent modulo f of x. So, what are we trying to do? We are looking at a ring of polynomials. What is a ring? Ring is a set of elements with certain properties. including additive inverse, associativity, and distributive properties, 0 and 1 being contained in the set, and so on and so forth. It follows the first 7 of the 8 properties required for a Galois field. So, we are now talking about this ring. So, this capital F of x divided by f of x, this shows that everything taken modulo f of x. This is a notation because the numerator is a set. So, this is called the ring of polynomials over f of x modulo small f of x. This is the notation, and we will be using this notation. Now, under some special conditions for f of x, the small f of x, this ring actually translates to a field. So, let us consider this ring again, capital F of x divided by this polynomial x squared plus x plus 1. Again our arithmetic will be over g of 2. So, this ring will have polynomials with highest degree 1. Why? Because whatever be your collection of polynomials, when you take modulo x squared plus x plus 1, the highest power can be at best x raised to power 1. So, what are the polynomials possible here? Well, there are only 4 possible polynomials here. So, let us look at it with a small example. What we are trying to do is take this f of x and take all the polynomials modulo this. So, we have not put any restrictions on how big this set is. You can have infinite number of polynomials here, you can make them as large as possible, but I will take each one of them and divide by x squared plus x plus 1, and whatever is the residue is the set which I am looking at. And if you look at this, the residue will be some polynomial with a coefficient times x plus another coefficient times x raised to the power 0, which is nothing but x plus. Now, since we are looking at GF2, we will have 2 possibilities for this location, either a 0 or a 1, again 2 possibilities 0 or a 1. So, we can have at most 4 distinct polynomials here. Which are they? 1x plus 1, 1x plus 0, 0x plus 1, 0x plus 0. And if you write it out clearly, we are looking at the polynomials x plus 1, x 1 and 0. Now, this is a finite set. So, from an infinite set, just because we took this modulo f of x operation, we ended up with only 4 distinct polynomials. Now, they can be added, multiplied, subtracted as we want, provided we are following this rule. Now, if you go back to the slides, we see that this ring contains 2 raised to the power 2 is equal to 4 elements, and each element is a polynomial. Please remember that elements can be anything, and here we chose them to be polynomials 0, 1, x and x plus 1 like we just saw, and we can try to build the addition and multiplication table for this one. So, I can add and multiply. So, this is the addition table and this is the multiplication table, and you can check that there is a 0 in every row and column, which shows that there is an additive inverse for each of the 4 elements. But if you try to see for 1, there is a problem because a multiplicative inverse is not necessarily present. So, therefore, what we would like to do is go to another example. So, now we look at another example, f of x divided by this polynomial x squared plus 1, again defined over g of 2, and again the elements will be 0, 1, x and x plus 1, and again I can write the addition and multiplication tables for these two. And what we look at it is that the first example of f x divided by x squared plus x plus 1 was actually a field, whereas this one is just a ring because of the absence of a multiplicative inverse. If you see this multiplicative table, x plus 1 does not have a multiplicative inverse, whereas every other one has a multiplicative inverse. So, each element 0 is of course excluded from a multiplicative inverse, but x plus 1 element does not have a multiplicative inverse. On the other hand, if you look at this ring, each one, so x is a multiplicative inverse of x plus 1, and 1 is a multiplicative inverse of 1, and x is a multiplicative inverse of x plus 1, and so on and so forth. So, you have additive inverse and multiplicative inverse for every element, and therefore, this ring is actually a field, whereas this ring remains a ring. So, what is interesting is this f of x, small f of x, sometimes ends up giving us a ring and sometimes ends up giving us a field. So, f x divided by x squared plus 1, this is not a field, whereas f x divided by x squared plus x plus 1 is also a field. So, now we come and connect these two concepts about why one gives a field and the other one does not give a field. So, let us explore what properties of this f x lead us to generating a field. So, the condition that we will soon see is that this polynomial f of x must be irreducible, which is in layman's language non-factorizable. We cannot factorize it, but let us see what do we mean by that. So, we define a polynomial f of x in capital F of x, which is a set of polynomials, is said to be reducible if f of x can be written as a product of two polynomials, where a x and b x are elements of f of x, right. So, now if f of x is not reducible, then it is called irreducible. So, if it is not factorizable, then it is means that it is irreducible. Over and above, if with this non factorizable irreducible polynomial happens to be monic, the leading coefficient is 1, then it is also called as a prime polynomial. Okay. So, a monic, additional condition of being a monic makes it a prime polynomial. So, a monic irreducible polynomial is a prime polynomial. So, factorization, some of the facts we know and we can quickly go over it. So, a polynomial f of x has a linear factor x minus a if f of a is 0, this we know, and then polynomial f of x in capital F of x, set of polynomials of degree 2 and 3 over g of q is irreducible if and only if f of a is not equal to 0 for all a in g of q. So, we can quickly test these out, and over any field we have this general expansion x raised by n minus 1 is x minus 1 times x raised by n minus 1 plus x raised by n minus 2 up to x plus 1. Okay. So, what we do is we quickly go over the next two slides and looking at that this ring of polynomials f x divided by f small f of x is a field if and only if this small f of x is a prime polynomial, that is a monic irreducible polynomial. It cannot be factorized over the g of q we are working at, and the proof is pretty simple. To prove that a ring is a field, we must show that every non-zero element of the ring has a multiplicative inverse, and that is what we do here, and we can show that the greatest common divisor GCD of two polynomials f of x and s of x can be written as follows, and then we show that since f of x is irreducible in capital F of x, we can write the GCD of f of x and s of x as 1. Now, we invoke the properties of residue and we do some basic maths, and we can easily verify that you can indeed have the condition of a multiplicative inverse. So, the theorem had if and only if. So, the only if part can be proven like if you have f of x has a degree 2, at least 2, and is not a prime polynomial. This is the assumption, and then we will contradict this assumption. Okay. So, we know that a polynomial of degree 1 is always irreducible. So, we can write this f of x as some r of x plus s of x for some polynomial r of x. Okay. And then we look at this ring f of x divided by small f of x, then a multiplicative inverse r inverse x exists, since all the elements other than 0 should have a multiplicative inverse, and then we substitute this here. So, r of x r inverse s of x here, and we do some basic maths, and we have assumed s of x is not equal to 0, which leads to a contradiction, implies that the ring is not a field. Therefore, we get this proof for irreducibility. So, let us look at the example which helps us understand the theorem slightly better. So, let us consider this polynomial p of x, which is x cubed plus x plus 1 over g f 2. Now, this is a prime polynomial, but we would rather verify that it is a prime or not. So, it is very easy. Let us see whether there are any linear factors. So, just substitute 0 and 1 because they are the two elements. If you substitute p 0, you get a non-zero answer, same with p 1, non-zero answer. So, there are no linear factors of the type x minus 1 or x, and this is monic, and therefore, p f x is a prime polynomial. So, now what we can do is we will shortly learn to construct extension fields using subfields. For example, we have g f 2 and we can construct g f 8 using this prime polynomial. Please note that if you have capital F of x divided by p of x, then the highest power is 2. So, let us look at this example. If we look at f of x and we divide it by p of x, please note that p of x is nothing but x cubed plus x plus 1. So, anytime I take the residue, the highest power can at most be a square. So, all polynomials are some coefficient square plus some coefficient x plus some coefficient. Now, we are working over g f 2. Consequently, this is a 0 or a 1, 0 or a 1, 0 or a 1, and therefore, you have got these 8. So, you can have these places filled up right from 0, 1, x, x plus 1, and then you have x square plus 1, x square plus x, and x square plus x plus 1. So, you have got these 8 elements. These 8 elements basically form elements of g f 8, and we will show that we migrated from g f 2 to g f 8. Now, we come back to the slides and we say that it is easy to construct the addition and multiplication tables for this field. Now, we do a few observations because we should not forget our end goal, which is to link it to cyclic codes, and we are almost there, just a few more mathematical tools and then we are ready to go. So, please note that x raised by n is equal to actually 1 modulo x n minus 1. So, this x raised by n minus 1 will become a very interesting polynomial for us. Now, we first make our link. Any code word can be uniquely represented by a polynomial, and how do we do that? Well, suppose my code word is C1, C2, C3 up to Cn, then we can write it very easily as C of x as C0 plus C1x plus C2x squared up to Cn xn. So, here of course, I did not start with a C0 which is missing, but if I remove this C0 here, so C1x, C2x squared and so on and so forth up to Cn. There are total n elements here n plus 1. So, we can choose to either go from C0 up to x raised by n minus 1 or C1 to x raised by n. Either which way we will have n elements, n coefficients corresponding 1 to 1 to the elements of the code. So, if you have for example over GF8 the code word C equal to 207735, well, you can always write it 1 to 1 for this. So, here there are n equal to 6, the block length is 6. So, highest power I need to go is n minus 1, and clearly this is the unique representation of this code word in terms of a polynomial. So, from this point onwards we will refer to code words as code word polynomials, because for cyclic codes it is very easy to say that. Now comes the most important link. Why are we talking about polynomials for the past so many minutes? Firstly, multiplying any polynomial by x corresponds to a single cyclic right shift of the code word element, because simply you are increasing the power of x by 1, and so it results in a cyclic shift, right. More explicitly in Rn, by multiplying Cx by x we get, so C0 which did not have a coefficient x now have C0x, the C1 was coupled with x raised to the power 1, now it gets x squared. So, you just simply shift, and this Rn means take modulo xn minus 1, x raised by n minus 1. The moment you do x raised by n minus 1, this highest power which became n goes back to the front. So, it is a cyclic shift. This is the property of doing modulo x raised by n minus 1. Please recall that x raised by n is equal to 1 if you take mod x raised by n minus 1. So, this will be our staple for the next few slides. All operations, all products, additions would be done modulo x raised by n minus 1, because that puts us in the domain of cyclic codes. So, any polynomial modulo xn minus 1 can be reduced simply by replacing the xn by 1, xn plus 1 by x, and so on and so forth. So, this is the critical observation. So, now we are back to cyclic codes. A code C in Rn, so Rn means we will take modulo xn minus 1, is a cyclic code if and only if C satisfies the following condition: f of x divided by small f x is in Rn. So, Ax, Bx if are two elements of C. What does it mean? Well, C is a code is a set of code words. Now, my code words are now code word polynomials. So, Ax is one code word polynomial, Bx is another code word polynomial. Sum of two code words is also valid code words. Not a surprise, because C is a linear block code. And if Ax is a code word and Rx is some polynomial, then Ax into Rx is also a valid code word. Okay. So, let us understand this thing. So, the first part is very simple, sum of any two code words is also a valid code word. The second part can be understood simply as follows. Well, if you look at multiplication of a valid code word with Rx, then it is nothing but Rx is nothing but a polynomial given by this. So, individually when I multiply, I can say okay, first we take Ax and I multiply it with R1x. Well, what is multiplication with R1x? One cyclic shift, but we know cyclic shift of a valid code word is another valid code word, and then I multiply this valid code word Ax with R2 x squared. X squared means 2 cyclic shifts. Well, 2 cyclic shifts is also a valid code word, and so on and so forth. So, Rn xn pertains to n cyclic shifts and multiplication by a scalar. So, each of these operations is leading to a cyclic shift of Ax, which is a valid code word. So, each of this operation is transforming Ax into another valid code word, and sum of all these code words is a valid code word, because sum of any two code words should be a valid code word for a linear block code. Consequently, the product of Ax into Rx should be a valid code words, hence should be an element of C. That is the proof. So, now we have a very simple way to generate cyclic codes, because in the previous slide we observed that this product of some valid code word with any arbitrary polynomial is a valid code word. So, can we have a notion of a generator polynomial, which when multiplied with an information polynomial gives a valid polynomial? That is the basic idea. So, how do we generate cyclic codes? Take a polynomial f of x in Rn, obtain a set of polynomials by multiplying fx by all possible polynomials in Rn. Remember, Rn is modulo x raised by n minus 1. The set of polynomials obtained above correspond to the set of code words belonging to a cyclic codes of block length n. So, let us take a simple example. So, let us take Rx is equal to R0 plus R1x plus R2x square, and we are doing it over GF2. So, we have got a total of 8 polynomials, since we are taking fx divided by x cube minus 1, which means that the highest power of this residue can be squared. So, there are 8 possible polynomials, okay. And then we can multiply each one. So, if you say x square plus 1, you multiply by 0, you get a 0, by 1, by x, and so on and so forth. You can try out all the possible combinations, and then you get only 4 distinct code words coming out of it. So, just now you generated your first cyclic code using this notion of multiplication of a polynomial over R3. What are these 4 distinct code words? The 4 distinct code words, as we just now saw, are 0, 1 plus x, 1 plus x square, and x square plus x. So, these can correspond to these 4 code words as we know in terms of the binary digits, and you can check whether they are linear block codes and whether they follow the cyclic property. So, with that we come to the end of today's lecture. We have understood what do we mean by a ring, specifically a ring of polynomials, and how and when a ring becomes a field. Then we had a detour into polynomials, how do we add, multiply, subtract and divide, and then we linked it up to cyclic codes. Well, we just have scratched the surface. Now that we have these mathematical tools ready, we are ready to explore this domain of cyclic codes. We have of course looked at a few examples. With that, we come to the end of this module.